Another day, another educative, because an educative day keeps unemployment away. Let's go around this pattern. So it's similar to two-pointer pattern, fast and slow. Two pointers traverse an iterable data structure at different speeds. It's usually used to identify distinguishable features of a directional data structure, such as a list or array. The pointers can be used to traverse the array or list in either direction. However, one moves faster than the other. Generally, the slow pointer moves forward by a factor of 1, and the fast pointer moves by a factor of 2 in each step. However, the speed can be adjusted according to the problem statement. Unlike the two-pointer approach, which is concerned with data values, the fast and slow pointers approach is used to determine data structure traits using indices in arrays or node pointers in linked lists. Give me a second. I think this is the main thing. Unlike the two-pointer approach, which is concerned with data values, the fast and slow pointer approach is used to determine data structure traits using indices. It's concerned about values, individual values, but this is concerned about traits of the data structure. That's noteworthy. So values versus of individual entries versus characteristics of the whole. Sex tag is in a given data structure. It's noteworthy. So it's also known as cycle detection algorithm. The key idea is that pointers start at the same location, but they move forward at different speeds. If there is a cycle, the two are bound to meet at some point. True. To understand the concept, think of two runners on a track. While they start from the same point, they have different running speeds. If the racetrack is a circle, the faster runner will overtake the slower one after completing a lap. Yes. On the other hand, if the track is straight, the faster runner will end the race before the lower one, hence never meeting on the track again. The fast and slow pointer pattern uses the same intuition. So two runners, right? Moving. Fast jumped by 2, slow moved once in the single step, fast jumps again, slow move once, slow is gonna be here while fast is gonna skip here and here and land there. So that's a cycle. It's a cycle detection algorithm. A problem that can be solved with this approach. Find the middle node of a linked list. True. Set them to the head of the linked list. Traverse the linked list by moving the slow pointer 1 node forward and the fast pointer 2 nodes forward. Once the fast pointer reaches the last node, the slow pointer has reached the middle of the linked list. That is true. So, yeah, once you reach the end, you've hit the middle. Interesting. Once you hit the end, you've reached the middle here. So, determine if an integer is a happy number. A step represents calculating the sum of the squares of the individual digits of the integer. Sum of the squares. Okay. I don't get this. A step represents. What does that even mean? Calculating the sum of the squares of the individual digits of the integer. Squares of individual digits. Okay. The slow pointer moves 1 step, and the fast pointer moves 2 steps. The process is repeated until either the fast pointer becomes equal to 1, in which case the initial integer is a happy number. Otherwise, if the fast pointer and slow pointer has made a cycle as in a pattern of numbers, so the initial integer is not a happy number. In this example, the fast pointer eventually becomes equal to 1, so 19 is a happy number. So start with a 19. The sum of the squares of the individual digits. Square of 1 is 1. Square of 9 is 81. 81 plus 1 is 82. Okay. Square of 2 is 4. Square of 8 is 64. 64 plus 4 is 68. Square of 8 is 64. 6 is 36. That sums up to 100. Do it again here, and you get 1. Oh, okay, that's interesting. Like I guess I was just tired yesterday. So does my problem match this pattern? Yes, if either of these conditions are fulfilled, either an intermediate step or as a final solution, the problem requires identifying the first X% of elements in a linked list. Okay, as a final solution. So either as an intermediate step or a final solution. I think that's noteworthy. The problem requires identifying the first X% of the elements in a linked list. Okay, so if you wanted to find the first, like, 25% of elements in a linked list, you would increase the fast pointer by 4. You would hop like 4 times, so that when it reaches the end, it's already the slow pointer will be at the 25% mark. I can imagine that example. The element at the k-way point in a linked list, for example, the middle element or the element at the start of the second quartile, etc. The kth last element in the linked list. This is interesting because in the 2-pointer problem we were supposed to remove, actually in this problem, it was a 2-pointer problem, remove the nth node from the end of a list. So I guess it's a precursor to the fast and slow pointer. But in that case, I was moving the fast pointer, all the way to the end first. Then how did that work? I think, yeah, I moved it all the way to the end. Let me open up the Scala draw. It was, where was it? I think it was here. Nth node from the end of this, yes. So we start, how did I explain it? Oh yeah. We move it, whatever n is, n times. We move the right node n times, right? And then we move both of them one step by step until the right node reaches the end, and then you add nth times from the end of the list. Okay? Solving the problem requires detecting the presence of a cycle. Solving the problem requires detecting the presence of a cycle in a sequence of symbols. No, if either of these conditions is fulfilled. The input data cannot be traversed in a linear fashion, that is, neither an array nor a linked list nor a string of characters. The problem cannot be solved with 2 pointers traversing an array or linked list at the same pace. Can be solved, in which case you do a 2-pointer problem. So real world problems, that's always nice to know. Curious what real world problems are in the 2-pointer section. Many problems in the real world use fast and slow pointers. Let's look at some examples. Symlink verification. Fast and slow pointers can use the symlink verification utility in an operating system. A symbolic link, the shortcut to another file. Essentially, it's a file that points to another file. Symlinks can easily create loops or cycles where shortcuts points to each other. To avoid such occurrences, a symlink verification utility can be used. Similar to linked lists, fast and slow pointers can detect a loop in the symlink by moving along with connected files or directories at different speeds. Compiling an object-oriented program. Usually, programs are not contained in a single file, particularly for large applications. Modules can be divided into different files. Yes, dependency relationships are then defined to specify the order of compilation for these files. However, sometimes there might be cyclic dependencies. Node usually gives this error when you have cyclic dependencies. That can lead to an error. Fast and slow pointers can be used to identify and remove these cycles for seamless compilation and execution of the program. Interesting, I've faced this before. So that's how it works under the hood. Good to know. I'm curious what real world applications were for the 2-pointer problem. Let me see. Transmission errors. Okay. Many problems in the real world use 2-pointer pattern. In a network protocol, response packets take the same route in reverse back to the source that the request packet took to the destination. Sometimes the path may differ due to errors, and we can tolerate at most one diversion, at most one change. Similar to the valid palindrome question I did. The path, in terms of IDs of routers along the way, is recorded. Now the issue is with all these real world problems is they're already solved, right? I'd probably just use a library to do it. I wouldn't implement it from scratch. Still, it's good to know why it's useful. The path, in terms of the idea of the router, is recorded in an array present inside the packet. And this is me hoping I'm recording. Okay. In an array inside the packet. 2 pointers can be used to determine whether the same path is followed from the source to destination, from destination to source, to identify the paths with more than one diversion router. So our topology remains intact and transmission errors are detected. Product suggests while shopping online, you may view a cart and current total doesn't qualify for free shipping. We want to show them pairs of products that can be bought together to make the total amount equal to the amount required to be eligible for free delivery. 2 pointers can be suggested pairs that add up to the required cost for free shipping. I would have liked a problem like this actually. It would have been nice to solve. Maybe it exists in the challenge itself section, you know? Yeah. Maybe not. Because this one's harder to think about. Okay, I imagine you sort the array by price, and then use a pointer on the top and end of the possible products to know that, oh, if what's in my cart plus what I can pick from is smaller than what I need, increase the cheaper pointer. If it's too much, reduce the expensive pointer. Okay, makes a ton of sense. All right, that is clear to me. I wouldn't do this. This is kind of a waste of time. If not that I'm exploring uploading things to YouTube. And because of this intro, I might just do one problem today and not do any other. Yes, because I have to get to work. It's already 9:23. If I start late, I end up finishing late. But this is such a great application. Actually, it's highly relatable. Super relatable. Strategy time. Match the problems that can be solved with a fast and slow pointer pattern. Select a problem in the left-hand column by clicking it, and then click one of the 2 options on the right-hand problem. Okay. Detect a cycle in the linked list. Yep, you just told me that. Identify if repeatedly computing the sum of squares and the digits of number this results. I mean, they just give me this exact example. Check whether a given string is a palindrome. That's the quality of the individual items, not the list as a whole, I think. Because data values, right, is data structure traits. The whole data structure. Okay. Relationship with each other versus. It's kind of a mixed bag, but is a palindrome somewhat a pattern? Reverse the words in a given sequence of letters. I wish this was above, not below. But yep, got it. First try. Love it. And I've gotten my streak for today, I think. Or someone was using my app online, and so I already have today's streak, because today is the 14th and it's already marked. Anyway, happy number. Try to solve the happy number problem. So write an algorithm to determine if a number n is a happy number. Okay. Use a function to check if a given number is a happy number. Starting with the given number n, replace the number with the sum of the squares of its digits. If number equals 1, which they picked, and repeat the process until the number equals 1. It's a happy number. If there is a cycle, so we pick that the given number is not a happy number. Interesting. Turn true if it's a happy number, false if it is not. Now, why do I want to know if a number is a happy number? in real life, I don't know, but it's useful to practice the pattern. So n is 23, start with 13, you add the square root to just go divide by n for the next iteration. 13 gives you 10, 10 gives you 1, yay, happy number. 2 gives you 4, 4 gives 16, 16, 4 gives 16, okay, 16 gives 37, 37 gives 58, 89, 145, 42, 20, 4, that's a cycle. 2 is not a happy number. That is funny. Test your understanding of the problem. Let's take a moment to make sure you have correctly understood the problem. Is 28 a happy number? Ooh, this might be hard to do. Okay, 4 plus 64 is 68. 68, we have 64 plus this 100. Yes, it's a happy number because we're on about 1. Yep. And then is 4 a happy number? I mean, I just saw this. No, it's not. Comes back to 4. You have a game for it. Arrange how to solve the problem. If fast is not 1. Also not equal to slow. Alright, initialize. Usually initialize is the first word in these things. With the input number of fast to the square sum of the input number's digits. If fast is not equal to 1 and also not equal to slow, increment slow by 1 iteration, fast by 2 iterations. Set slow to the sum of digits, sum of digits to sum of digits. If fast converges to 1, return true, otherwise return false. Actually, that's the answer. Yeah, I'm sure. Alright, showtime. Then you may build on to solve this problem. Sum of square digits. No, this is a nice helper. Hope I didn't. Let me reset this thing. Alright, it's a new section. It's fast and slow pointers. Create a new folder. And then what's it called? Happy number. You know, all these things I'm doing, I could have been able to solve this if educative existed when I was younger, and then have this done. But better late than never. Once you do it once, I mean, it's with you, given the rest of your life, pretty much. Alright, so this is what that does. Well, number is greater than 0. Sum of square digits. Does the floor. Okay. Of the number divided by 10. The digits. Number modulo 10. Honestly, writing this is not what's important to me right now. But that's a nice helper. I think I know what it does. Just takes a number and sums the digits, individual digits. So temp total sum. Interesting. Seems nice. Probably need to walk through the burger to fully understand that, but I don't need to fully understand that because abstractions, yay. Okay, yay for abstractions. Is happy number. Okay, so what did they say? What is my strategy? Initialize the variable slow. with the input number and fast with the squared sum of the input numbers digits. Okay. Oh wow. Copilot knows what's up. Copilot knows what's up. Actually, no. Copilot has no clue what's going on. While slow is not equal to fast. Let's see. If fast is not 1 and also not equal to slow, increment slow by 1 iteration and fast by 2 iterations. Okay, I think Copilot is gonna walk me through it, but let's find out. If slow and fast are not the same, right? Do that twice. Nah, Copilot has no clue. It's wilding on me. This is rubbish, complete and utter nonsense. For now, developers still have our jobs. Because honestly, if you can prompt well enough to make this super useful, like perfectly useful, then you can code well enough to not need it. Still, it makes you faster. If fast is not 1 and also not equal to slow, increment slow by 1 iteration. Fast by 2 iterations. So if fast is not 1 and not equal to slow, if slow and fast fast is not 1. Does break. I think I should return false. No. If fast is equal to 1, return true. Then while it's not the same, but if it becomes the same, then turn false. Is that it? I don't know. It's worth a try. Seems super easy. Probably wrong though. Oh, mostly right. How about that? Oh, it started off as 1, so I need to add that case. What happens if I just move this up? Okay, still don't work. Honestly, 1 is a happy number. I'll just say if fast is already equal to 1, or if I want to be really quick, right? Or for efficiency, just put this as the very first thing. If n is equal to 1, return true. No need to define all these variables and do all these things. Just save yourself quite a bit of time. Right, seems simple enough. Oh, nice. We can call it a day. This looks so good. That makes me feel happy. Very delightful UI. Okay, and that's it for today. How are we doing on time? 24 minutes. Glory to God. Solution, happy number. Statement, solution, naive approach, optimized approach, step by step. That's lots of stuff. I know this. A solution. What's a naive approach? Calculate this in a hash set. Oh wow. Why would I do that? Square sum of digits. store the computed sum in a hash sense. You know, honestly, they call it naive, but that's probably how it was the standard approach at some point in time. Calculate the squared sum of digits of the input number. The sum is already present in the set. If yes, we take a side project or false. Oh, I didn't even think of the big O notation of this. I mean, in the worst case, it'll go through the list once, and I didn't do any drawing, but bear with me. In the worst case, it'll go through everything, loop through this, run this math once. Actually, is there even a way to say it? What's the longest possible path to a happy number, really? I can't say. And I'm not looping through like a predefined list. So can I say it's a big O of n? The input size is 1, right? So, and that one, I don't know, I'm actually curious. Maybe I'm tired. Log of n, okay. Space complexity is log of n, since we're additional space to store our calculated sums. Then I just did this thing. I already did that. Oh wow. Okay. What are they saying? Oh, they didn't use the helper function. It's true, I used the helper function. It actually took away a lot of thinking from me. Okay. Honestly, I'm just interested in the time complexity. The worst case is given by the case of a non-happy number. Okay. Since it gets stuck in a cycle, as a happy number quickly converges to 1. Quickly. How do you know quickly? How do you know it always happens quickly? Sum of digits of the sum. In fact, what's the quality of the input number? What are the traits? Okay, it's less than 2 to the 31. That's a magnificent number. It's given by the case of a non-happy number, since it gets stuck in a cycle. That's a happy number. Sum of all the digits in a number, because the number of digits in a number n is log to base 10. Ooh, that's a math thing. The natural logarithm. The logarithm to base 10, not the natural logarithm. Okay, that is true. Actually, because we count in base 10. Log of n. Okay. Before delving into the detailed complexity analysis, let's first consider the largest possible next number for each given number of digits. To estimate the count of numbers in a cycle. So, oh boy, this is like the most involved time complexity. To estimate the count of numbers in a cycle, it's going to get number 3 digits. The RCD number is 999. The sum of the squares of the digits is 243. Therefore, for a 3-digit number, no number in the cycle can go beyond. Okay, makes sense. Yeah. 243. Therefore, the number complexity in this case is the maximum number. think I'm too tired to fully grok this thing, but it's not. Doesn't seem complicated at all. For any three-digit number in the cycle can go beyond. Times 3. I wonder why times 3. Where this is the amount of digits in a cycle of numbers in a cycle, and 3 is the number of digits in a 3-digit number. This is why time capacity. The 3 digits comes out to be O of 1. For number more than 3 digits, any number of more than 3 digits will lose at least 1 digit at every step until it becomes a 3-digit number. For example, the first 4 digits we can get in the cycle is this: the sum of the square of the digits in this. Oh wow, it takes that long. Any number with more than 3 digits can be expressed as, again, log of n, log of n. Since log of n is a dominating term, I'm gonna try to use this. Okay. Kind of makes sense loosely, not concretely. That's fine. The total time complexity comes out to be O of 1 plus log of n, which log of n wins out. So then space complexity is O of 1. Because I'm only storing 2 variables, and that doesn't change no matter the size of the number. So yeah, this is good. It's happy. It's looking good. Still 4%, but we are done for today. Thank you so much.